everyone. So I'm unexpectedly out today, obviously. So we were going to go through the sheet together. I'm still going to have you work on it, but I'm going to give you some hints for each one because these are the types of things that would come up as you were working on it and we talk about together. So let's do this quick. Okay, so I will put little timestamps in the description of this so you can skip around to get to the problem that you want to get to. But I'll just go through kind of one at a time. And again, I'm not going to go through the whole solution for each of these, but I'm just going to kind of go through like the main idea and give you some hints for some things. Okay, so 1A asks you, what would the force of gravity be acting on a 1,500 kilogram satellite like that's on the surface of the moon? Well, if it's on the surface of the moon, you can use the gravitational field strength for the moon, which is little g for the moon, and it tells you what that is. You know, force of gravity equals mass times little g, so there you go. That one's quick and easy. All right, 1B. All right, now it's telling you, all right, the satellite's orbit is going to be 100 kilometers above the surface of the moon. So be careful, again, when you're measuring orbital or the radius for finding the force of gravity, you need to measure to the center of mass of the objects. So you need to take that 100 kilometers, add it to the radius of the moon, and that would be the radius of the orbit for the satellite. All right. Also, please be careful. Remember, whenever we're doing calculations, everything needs to be measured in meters, seconds, and kilograms. And if it's not, make sure you convert it to those before you do the calculation. So here it gives you the altitude in kilometers. You'll need to convert that to meters before you find the orbital radius. Okay. 1C. When the satellite is in orbit, how big will the centripetal force be? Okay, so quick, here's a free body diagram of the forces acting on the satellite when it is in orbit. For any object that's in orbit, there is only the force of gravity acting on that object, pulling it towards the object that it's orbiting. So if the satellite is orbiting the moon, you're only going to have the force of gravity pulling on the satellite directly down towards the moon. So you'll get just like this, which means the net force acting on the satellite is equal to the force of gravity, and that's it. That's the only force acting on things that are orbiting, which is useful. Okay, so when it's in orbit and it's asking how big the centripetal force will be, well, up to this point when we've been calculating centripetal force, typically what we've done is we said like, okay, centripetal force is like the net force, and it's equal to the mass of the object times its velocity squared divided by the radius. But like it says here, we don't know the velocity of the satellite. So we can't use this equation. But we do know that the net force is equal to the force of gravity. Okay? So at this point, you're like, here's the mistake you'll make, or that you'll think of first, which is incorrect. She's like, oh, the force of gravity acting on the satellite. I know that. That's going to be this number up here from 1A. But no, it's not, because that's the force of gravity acting on the satellite when it's on the surface of the moon, not when it's in orbit. All right, and then it's another 100 kilometers above the surface. So instead of using mg to find the force of gravity, you have to use the law of universal gravitation and use g times the mass of the satellite times the mass of the moon divided by, ooh, that's messy, the radius squared. All right, don't forget to square the radius. Be careful with how you enter those numbers in, but you can use this to find the force of gravity acting on the satellite, and because that is the only force acting on the satellite, that is the centripetal force, or the net force acting on the satellite. Okay, now it's saying, all right, find the required orbital velocity for the satellite. Well, again, we know that the force of gravity equals the net force. So we also know that the net force for something that is orbiting is mass times velocity squared divided by the radius. So when circular motion tells us this, we have velocity there. And now we didn't know the velocity for 1C, But now that we have the value for the force of gravity for 1c, you can just say that, okay, well, the net force equals mass times velocity squared divided by radius, and the net force equals the force of gravity, therefore the force of gravity has to equal mass times velocity squared divided by the radius. And in 1c, you found that force of gravity for the satellite in orbit. So now you know the mass of the satellite, you know the radius, you can find the velocity squared. Okay? All right. Let's see. Here we go. How long, 1e, how long will it take the satellite to orbit its moon? And this is called the orbital period. All right, this is definitely one we would go over in class a little bit because you kind of have this equation on your equation sheet, but it's not written in this way. So we would have needed to talk about it a little bit. We have used this relationship before when we did some circular motion, actually with the When Pigs Fly lab. But when you are finding the velocity for something moving, in a circle with uniform circular motion, all this is displacement divided by time, okay? Because 2 pi r is the circumference of a circle, all right? And this is capital T is the period or the time it takes an object to make one complete circle. So it's basically saying here is, how long the path length of that circle is, and T is the time it takes to travel that path length, which is the same thing as change in position divided by change in time. So you can use this equation to find the orbital period. Just rearrange that equation to solve for the period. You know the radius, you know the velocity, you just gotta do that, all right? Okay, is this satellite accelerating when in orbit? Well, I will tell you the velocity is constant, or sorry, let me restart. In this one, I will tell you the speed is constant, right? When you find that speed, it's constant, but just think of circular motion, what's always happening in order to keep it moving in a circle. And then when you are trying to find the direction and magnitude of the acceleration, remember we're talking about acceleration, centripetal acceleration, which there is an equation for that's on your equation sheet. So if you're stuck, look at that. All right, 2. All right, the space shuttle aims for an orbit 250 kilometers above the surface of the Earth. All right, real quick, it gives you kilometers here. Make sure you convert that to meters. Be real careful here. It gives you Earth's radius in kilometers. Convert that to meters there. Otherwise, things will be messy. And again, remember when you're finding the radius of the orbit, you have to add those two things together to get that radius. Okay, so you are going to use this equation to find the orbital speed of the space shuttle. And right now, you're watching this and saying like, okay, but where the heck did that come from? Where is that on our equation sheet? And it's not, at least not in this form, because let me show you where this comes from. Like we said earlier, when something is orbiting, the only force acting on it is the force of gravity, all right, which means that the net force acting on the space shuttle in this case is equal to the force of gravity acting on the space shuttle by the Earth. Okay, so we know in circular motion that net force is equal to the mass times velocity squared divided by the radius. And we also know that the force of gravity acting on the space shuttle, which is something that is in space and it has mass. Well, let me do it like this, because this is where people can get into trouble. So I'm going to actually erase this. Make sure you're really careful with your masses here. All right, because when we're talking about the net force, this is the net force acting on the space shuttle. So therefore, this is the mass of the space shuttle. And now when you're using the law of universal gravitation, we'll take the mass of the space shuttle times the mass of the Earth divided by the radius squared. And this is the orbital radius. Okay. Now, if you look at this, you can do some canceling. So you see on the top of both, you have the mass of the space shuttle. So the mass of the space shuttle actually cancels. On the bottom, you have the orbital radius here, and you have the orbital radius squared here. So we can get rid of the squared and just have it once there. All right. And what that means now is when we rewrite this, you can rewrite it as velocity squared equals big G times the mass of the Earth divided by the orbital radius. And then just take the square root of both sides, and you get the square root of big G times the mass of the Earth divided by the orbital radius. Okay, so that's where that comes from. And again, this is the value of solving things symbolically. You can take this whole expression and you can plug all those numbers in and do the calculation to solve for the velocity. And if you do that correctly, you'll get the exact same answer, but it is going to be a lot easier for you to just do this thing right here. All right, so solve for the velocity symbolically because you know the net force is mass times velocity squared divided by the orbital radius. And you know the force of gravity is equal to big G times the mass of the space shuttle times the mass of the Earth divided by the orbital radius squared. Simplify that and solve for velocity, and you get this expression, which is a lot simpler than what you got over here and will make your life easier. So I would use this. Just make sure you know where this comes from and you know why it comes from there. Okay? This is the important part. Don't memorize this equation, but know where it comes from by knowing how to do this part. Okay, 2b, oh, I did a good job numbering this. All right, 2b, again, it asks for the orbital period. Here is the equation for orbital period. We talked about that above. So if you're not sure where that comes from, make sure you listen to what I talked about up here in 1e. All right, skipping to 5, because I can count. Earth's orbit around the sun is very nearly circular, with an average radius of 1.5 times 10 to the 8th kilometers. Again, make sure you convert that to meters. Hey, I did that for you already. But yeah, make sure you always use stuff in meters, seconds, and kilometers. Oh, no, not meters, seconds, and kilometers. Meters, seconds, and kilograms. Okay, 5a. Determine the average speed of the Earth in its orbit around the sun. So, in this case, you're going to use this equation. Again, if you're not sure where this equation comes from, this I explained in 1e, so go listen to that if you have skipped to here. But basically taking the circumference of the Earth's orbit and divide it by the period of the Earth's orbit. And just a hint, the period of the Earth's orbit is 1 year. Okay, well, you can't just put 1 year there. We need to convert this to seconds. All right, if you don't convert that to seconds, you're not going to get the right answer. Everything needs to be in kilograms, meters, and seconds before you do calculations. You can do this by hand, but just like ask Siri or Google to do this for you. Just put 1 year in seconds, you'll get it. It's faster that way. Okay, 5b. What is the magnitude of Earth's average acceleration in its orbit around the sun? All right, you're finding centripetal acceleration in this case. There's an equation for that. Just use that. 5c. Determine the gravitational force on the Earth by the sun. All right, there are two ways to do this. Okay? You can use the gravitational law here. You can do that. You need to look up the mass of the sun, and I guess it gives you the the radius of the orbit there. So you could do this, that would be fine. A second thing you can do is just use Newton's second law because you know the acceleration of the Earth. You know the mass of the Earth, or you can look up the mass of the Earth. I guess it's not posted here, but you can look up the mass of the Earth and you can do this too. So both of these will give you the same answer because the net force acting on the Earth is only the force of gravity, and that's that. Okay, those are all of my tips and hints. I hope you enjoyed this. Again, make sure you work on this. You should be good. I will hopefully see you soon. Bye.